So our last sponsor presentation for today comes from Alessandro Rigazzi from HPE, who's going to be talking about SmartSim. Alessandro.
Thank you, Brian. All right, welcome everybody. So yeah, my name is Alessandro Rigazzi. I am a senior AI and ML engineer at HPE, and I am one of the tech leads for SmartSim. So what is SmartSim? So first of all, it's better to talk about why SmartSim. So over the last more or less 10 years, there was a paradigm shift in numerical and scientific workflows. I say over the last 10 years because it means that like 10 years ago, I got my PhD using the old paradigm, and now I have to work with people who are using the new paradigm. So the old numerical workflows look like this. You have input data, which was like a set of initial conditions, a file representing a geometry for your CFD simulation, or maybe hard-coded values in your executable. You pass everything to your monolithic application, which used to be, obviously an HPC native application written in most likely parallel C, C++, Fortran with MPI, or some other technologies for multi-node applications, and then it would contain all the logic of your experiment. Like you would put everything you needed in one monolithic application. And then you would run it on the input data, and you would get the output data. And you would store it on the file system, and most likely visualize it and analyze it once. At least this is what I used to do. And everything you had to add to your workflow, to your experiment, you would just stuff it into the monolithic application. I don't know, you needed a new format for outputting the files, you would just write a converter into your application. You would always have basically one big run, which you would basically execute through bash scripts, and that would be all, right? You would write things to the disk, read them once, and that was all. And that's what I did. But now, when AI came into play, there was a big problem with this. Like, when you wanted to add something to your monolithic application, AI was running at a pace which was not comparable to that of numerical simulations and numerics in general. If you wanted to try to add the new AI technology into your simulation, into your monolithic application, you constantly had to add new things. You had to add new portions of the code to your build structure, and everything was falling apart. And so that's why people started moving away from monolithic applications and started working in a different environment. So in SmartSim, we are interested in whatever starts with an HPC parallel application, which is a simulation. It's a numerical simulation, and it's basically performing very well on supercomputers. And that's basically the first gear of your engine. That's what provides data to your workflow. And then what you have, well, basically maybe you want to have ML inference in your simulation because that's another component which now is very important. Or you want to train a model while you're running your simulation, or you want to do everything at once, or you even want to have visualization and analysis in real time. You maybe want to have in situ visualization, analysis. You want to maybe put something back from your analysis into the workflow. And that's what's happening nowadays, right? Workflows are like this, and every piece of the workflow, every gear in this drawing has a clear set of responsibilities which are different from the other portions of your workflow, right? You have the HPC parallel application, which just runs the simulation and maybe requests inference from another portion, right, from the ML inference part. The ML inference part just has a model, executes the model on the data, gives a result back. Maybe chooses the best model out of some models it has. The model training, which you could be doing during your workflow, is just accessing the data which is produced by the parallel application and trains in parallel maybe, and trains several models at the same time, selects the best one, and outputs everything and puts things back into the workflow. And visualization and analysis, again, maybe you render in real time. Maybe you're just analyzing things because you want to kill simulations which are going wrong, or basically are going to explode, or basically maybe you want to add some value that you can compute on data, but you don't want to have it in the parallel application. You want to compute it externally and put it back into the workflow because it could be some kind of flag indicating you're stepping out of a regime to get into another one. So initially, our approach was to say, okay, we know more or less these are the gears, these are the different applications people want to use. Let's just create some kind of application which you can basically fill the blank for, right? You can put the HPC parallel application here and then AI there and so on. But then we discovered that as in numerics, it often happens in numerics, everything was a bit snowflakey, right? Every researcher had a different idea on how to use AI. And that's why we had to basically quickly find something which would be flexible enough to accommodate different ways of using AI in numerical applications. So again, we tried to categorize AI usage in numerical workflows. This is not extensive. This is not something that covers all types of applications, but we try to at least have some kind of classification. And we start with ML in the loop, right, which is very close to the simulation. So we categorize AI based on how close it is to your basically numerical step, your simulation step, right? You have the machine learning in the loop. It's whenever you want to use an AI model to compute some quantities in your step, in basically your simulation core. Then we have ML on the loop. You maybe want to train a model on some kind of trajectories of your simulation, maybe because you know that it's not very important what happens on one single step, but it's more about where your simulation is going. Getting a bit farther from the simulation, we got to ML around the loop, which is basically, okay, I run a full simulation, I get the results, I train a model on that, and then I do something with the model. Finally, there is Edge AI, which is even farther. It's basically on a different system, on a different supercomputer. It could be that you have simulations running on one supercomputer, or maybe you have a lab which is getting data from some sensors, some telescopes, or whatever. And then you want to trigger something on another supercomputer or another system using AI. AI could be on the sender, it could be on the receiver, and still it would just be kind of a compound workflow spawning multiple simulation over multiple machines. And then on the other side, there is ML outside the loop. This is different because it's not basically when AI helps the simulation, but it's more when simulation helps AI. So basically, you want to train a model and you want to train it on the simulation. You want to steer the simulation so that it goes and computes samples in regimes you are not trained well for. So basically, a model which needs to be curious about the whole parameter space. So to basically accommodate all of these examples, we needed something very flexible, and that's what we came up with. Well, this is SmartSim. SmartSim is open source. You find it on GitHub. It's always been open source, and it will always be open source. It kind of bridges this divide between traditional and numerical simulation and data science. It provides a loose coupling. So we never wanted to have tight coupling. We only wanted to have loose coupling. Why so? Again, because we don't want to force users to integrate things in a tight coupling situation, because they want to be able to plug and play new portions of the workflow. They want to change the model. They want to change the toolkit they use to run the model, to train the model. They want to do things that if we try to do tight coupling, it won't work, right? So what we did was to basically place into the workflow what we call an orchestrator, or basically a feature store, which is a key value store, which can also execute AI models or machine learning techniques or code, basically active code on the data which is stored on the database. On the left-hand side, we could have the native C, C++, Fortran simulation running and just communicating data to the feature store, so sending and receiving data to and fro the data to the data store using the client we wrote. So as a feature store, we selected Redis, which has a good interface for AI, and we wrote a client for C, C++, Fortran, and Python to be able to use Redis with AI functions smoothly from simulation. So once the data is on the database, is on the orchestrator, you can access it from other components of your workflows. You can plug new components at any time. You can read data from the database. You can put something back, and so on and so forth. And this was the idea behind SmartSim. It enables several opportunities. You can set up, configure, run, monitor simulations from a Python script or notebook. So instead of using a bash script, basically you switch to a Python script, which is a bit more understandable and maintainable and portable, or a Jupyter notebook. It helps embedding machine learning and data analysis techniques in numerical simulation and exchanging data at scale. I will skip the rest for the sake of time, and we'll go just to some use cases and examples. So again, what we wanted to do with SmartSim was to allow researchers to achieve this kind of workflows without having to, for example, always touching the file system to exchange data. Because at the beginning of this revolution or this paradigm shift, researchers would just dump the output from one monolithic application to the file system, read it from another application, dump the results back, and do this forever. And that wouldn't really work with file systems. So a simple, basically archetypical example with SmartSim is just you have a cluster database, you start with a Python driver, which is the language spoken by SmartSim itself, and then you start the feature store. So SmartSim does this. It starts a feature store on some nodes, and it will run it on parallel so that it basically becomes a sharded database spanning multiple nodes. And then, for example, you could start running a climate application on some nodes and using SmartRedis, our client, to communicate to the database, and then start another application, again, which is running on parallel on other nodes, and using SmartRedis to communicate with the database. And by this, you obviously obtain loose coupling, and then you can plug and play other portions of the workflow. And on the database, you could also have active code running. You could have models and scripts to post-process the data, for example. So some examples of using AI in the loop. This is the first study where we collaborated with the National Center for Atmospheric Research in Boulder, Colorado. It's basically AI in the loop in this case. So yeah, this is the paper we published together. It was published, I think, in 2022, but actually the study was performed in 2021. And so what was the idea in this case? So the goal of this study was not to replace the numerical simulation with AI. We didn't want to create a big surrogate model which would just basically take numerics out of the equation, pun intended. We wanted actually to enhance the numerical simulation with AI. Why so? Well, MOM6 can run obviously on different grids, so on coarser and finer grids, but some quantities, such as the eddy kinetic energy, cannot be computed on coarse grids because coarse grids cannot, on coarse grids, eddies cannot be resolved, and so you need finer grids. But in production, basically, usually centers use the coarse grid. And so the problem was that on coarse grid, the model would fail because it wouldn't find the correct eddy kinetic energy. There were parameterized models or prognostic models where basically they tried to add some parameters to make sure that this eddy kinetic energy could be computed from other variables of the simulation. But those were not very reliable, especially on the coarse grid, which is used in production. And that's basically where we said, okay, if we're going to use a parameterized approach, it has parameters, it has kind of guesses on how the simulation is going because the simulation cannot capture some levels of details. Well, basically, why don't we just replace that part with an AI model, which usually is better at guesstimating or estimating something, right? And so we basically trained a neural network on the fine model, on the fine grid, so that on the fine grid we knew that it could resolve the eddies. It could basically compute the eddy kinetic energy almost exactly. And then we would use the same model, the same trained model, on the coarse grid, point-wise, so that it could access the same variables, but on the coarse grid. And that was actually a success. So here on the right-hand side, on the bottom right, you see that especially in these areas, our prediction, so the prediction of our model overlaps with the, with actually the so-called ground truth, which is the one computed on the eddy resolving grid. And these are exactly the areas our basically the co-authors were interested in. This was the state of the art before our paper. As you see, it tended to overshoot in this area and basically miss everything here. Here you see some structures are well visible here, and these are very close to the ground truth. Obviously, we are overshooting here. This is clearly seenable here, but that's fine because we weren't basically interested in that part. Our co-authors were interested in this part. So we ran this as an ensemble. So basically, SmartSim has this feature to run ensembles of simulations together, organizing basically the fact that the same variables from different ensemble members won't clash in the on the database without the need for the user to specify different keys or to store the data. We executed 12 ensemble members on 200 nodes. This was quite an old system. It was an XC50, a Cray XC50. And we ran the database on 16 nodes, which had one P100 GPU per node. We ran it for days, so stability was okay. And the accuracy was improved by 20%. And the overall performance only decreased by 10%, including the fact that we were running a large ensemble on the system compared to just one single execution of a simulation. In terms of code, what do you need to run a SmartSim-based experiment? It's very little code. So this is basically the definition of the experiment, which is the user-facing class in SmartSim. There are some settings which are standard settings for running on supercomputers, so like how many nodes you want to use, the time, and some more batch arguments you want to add. This was running on Slurm. Then run settings, things like how many tasks per node and so on, and then you add the files you need to copy to execute your simulation, and also files that you want to modify before the simulation starts to have some statistical meaning in running multiple ensemble members. Then you configure each ensemble member very quickly. And then you basically start the orchestrator. So with the feature store, you specify on how many nodes and so on and so forth. And then you generate and you start. And once you start, SmartSim first starts the orchestrator so that your data can always be stored on the orchestrator, and then all the ensemble. And that was it. And in terms of client code, so basically, we are well aware that HPC researchers and scientists don't really want to mess up with their code. They don't want to destroy their well-written and well-established code with a new library. So we try to be super minimalistic in what we require to access a workflow running through SmartSim. Basically, MOM6, which is the Fortran library used in this case, is 1,800 plus lines, and we only required 30 lines to include all of the SmartSim features into it. Here you see the core, starting the client, which is what is used to communicate with the orchestrator. Put in the tensor, so the tensor is basically the snapshot of your simulation at that moment with all the fields it needs to put on the database, defining the names of the output and the input of whatever inference you want to run with AI, and then run the model on the database using the tensor you have just put on it. Finally, you just unpack the result, so the inference result, and you use it in the next time step. So again, these 5 lines are basically what you have to do to compute inference and get the result back. We also ran at scale to check if everything was working correctly and scaling horizontally. We took one study by Guillaume and Zanne, and we ran it on Frontier. We ran several different, we ran it in different ways on multiple settings. And we always found that the cost was, basically most of the cost was in running the convolutional neural network, which was quite a beefy neural network. And in communication, it was 15%, again, on a very large number of nodes, which was required by the simulation itself. We just wanted to stress test our infrastructure. Another use case, which is interesting, is has been developed in Stuttgart by Kurz, Offenhäuser, and Beck. The idea is, again, computational fluid dynamics. In this case, is a turbulence model. So the idea is, okay, I want to run a CFD simulation, but I cannot afford running it on the fine mesh. So what I do, I separated the full solution into a coarse solution plus some turbulence model representing what's happening at the finest scales, right? This is an approach which has already been implemented, right? So the idea is that the turbulence model can be whatever you think it can be, right? In some cases, it's usually a parameterized model, for example, the so-called Smagorinsky coefficient. And that's, again, the same story as before, right? So since we are using some parameterization of the turbulence model, why don't we replace that parameterization and not the full simulation with an AI model? This was something that other researchers had done before. The problem was that if you trained offline, so basically you had a bunch of simulations, you were training your model, and then you were trying to use the model in another setting, in some slightly different regime, the model could not run on that regime. It would usually go, well, it would basically go NaN somewhere. So the idea of this team was to use reinforcement learning so that actually, while the simulation is running, they were training the model, the reinforcement learning agent, and they could tune the reinforcement learning agent to different regimes in the simulation, right? So basically, they were using SmartSim and the orchestrator as the centralized authority for the training of the agent, and using Flexi, which is a CFD library, to execute small trajectories of simulation, using the reinforcement learning model to predict the simulation and basically leaving the agent on the database so that basically inference could be computed from the database itself on the data produced on the workers. And every, well, thousands of steps, I think, they were just retraining the agent based on the new trajectories, on the new events. The results were very good. Like, they got very good overlap with direct numerical simulation and also with implicit large eddy simulation, but the cost was way less than using large eddy simulation or, well, let alone DNS, obviously. But there's something more interesting in this approach, is that the reinforcement learning agent can be trained on different reward functions to achieve different results. And in this case, for example, they use the same approach, the same setting, but they defined a different reward function, and they wanted basically to minimize the turbulence of this flow here. So here you see usual cylindrical obstacle, von Karman vortex street, and so on and so forth. This is the uncontrolled simulation, and here below you will see what happens if, by using a reinforcement learning agent, they use two jets, one here and one here, to basically add or remove momentum or add or remove energy from the flow. And I guess it will start like this. And as you see, the reinforcement learning agent basically minimized the turbulence here, getting to a more laminar flow in this area here. So they had like probes to check where the, well, to check the turbulence of the flow. There's another use case I won't go into too many details for. It's about using SmartSim to reproduce the deep drive MD use case. This is basically protein folding and training a model to do projecting the folded trajectories onto low-dimensional manifolds and so on. We did everything with SmartSim. Again, the feature of SmartSim is that data never touches the file system unless it's required to. So all of this workflow, all the workloads you've seen before and I showed before, they are all running without touching the file system. The database is in memory, all the data stays on the database, and only at the end of the simulation, if needed, the data can be stored. Why so? Well, because in this kind of complex workflows, users, scientists, researchers are not interested in the intermediate results of the workflow. They're interested in what's the input and what's the output of the workflow. Everything which is in between can be basically discarded at the end of the simulation. And that's what most likely is happening. And you don't need to store it on the file system and then delete it at the end of the simulation. So I'll use the last 5 minutes to just go through some closing thoughts and some of the other ongoing projects which are using SmartSim for HPC and AI. OpenFOAM, I have a dedicated slide for it, but basically we have been working with the OpenFOAM data-driven modeling special interest group to add SmartSim to OpenFOAM as a submodule. This can then, basically the idea is to let OpenFOAM users put their data through to SmartSim using only open foam code, open foam submodules. MFIX EXA is one of the exascale initiatives in the US. It's using SmartSim to train a neural network as a surrogate for multi-phase Lagrangian Eulerian solvers. MUM6, NEMO, CSM, these are all oceanography and basically climate simulation toolkits. They are using SmartSim. We are collaborating with them to create basically a general interface to allow for general users to have sandboxes to explore machine learning techniques. SimLint is a product of Excalibur, which is the UK exascale initiative, and they're using SmartSim to implement learn correction. And what we're working on currently is the support for HPE Dragon. HPE Dragon is another open source library developed by HPE, and it's for distributed computing. We are basically using it to start the jobs on the allocation currently, and we will then allow users to use workers through Dragon on supercomputers, allowing for more flexibility. The OpenFOAM submodule, there is a paper for it. It's going to be published in Mechanica, and there is a repo, and the preprint is available here. There are all the details about what we did. We implemented different types of AI-enhanced workflows or machine learning-enhanced workflows with OpenFOAM and SmartSim. One of the coolest, newest features of SmartSim is the dashboard. So it's a standard dashboard which can be launched on a browser and can be used to monitor the execution of ensemble members and data going to the database and so on and so forth. There is a documentation which is always up to date. If you don't believe me, just go to craylabs.org. We strive to keep it really up to date. At every new release, we go through it, and it contains everything you may need, including tutorials. We have Docker container tutorials, and we have a repository for SmartSim, one dedicated for the client, which is SmartRedis, and then here are other interesting links. If you happen to go and look at the repo, remember to star it so that you can always be informed about the latest developments. And with this, I will conclude my presentation. I'm ready for questions. Thank you.